Assalamu alaikum. So let me just send you the first link of the problem. So basically, we will start our session by the first concept, which will be sparse table. So in this problem, let us just take this problem for as an example to learn sparse table. Okay, so basically we have n elements, so n is up to 2 into 10 power 5. Then we have q queries, which are like they give you L and K. So basically all we have to do is to find for this L the maximum R such that the end of all of these numbers is greater than equal to K. So we have to find for this L maximum R such that the end of all of these numbers AL and like the bitwise end is greater than equal to K. So this is what we have to do, and we want to use, I mean, there might be some solutions without it. I don't know them, but we will try to use sparse table in this. So basically, let me first teach you what sparse table actually is. So if we had to just brute force this, or I mean, the main problem is to find, like, how can we first solve this problem? Let us just first analyze that. So if we have, we are sure, we know that like if we start from some point and keep adding numbers and we are actually ending them, let's say, I mean, if we just keep doing and as well as we are adding the numbers, we know that and will decrease, right? Because as we keep adding numbers, and cannot increase, because I mean, if our previous and was something like this, for example, then even if the new and is bigger than this, it will always be a subset of the previous one, right? Because all and does is just keep ones on those places on which there are ones already. So everything else will be actually zero. So it will decrease, or the next and will be less than equal to the previous and. Okay. So this is a common property of and, that it always decreases. So by this we can say that, like uh, for example, AL could be greater than equal to K, but as we go to the right and increase our R, or try to increase our R, we are decreasing the end, so there will be a point when it will become less than K, right? So basically all I'm trying to say is, since this is monotonic or like it is decreasing uh, linearly, we can do binary search on this. So if we can just do binary search on R and just say if the end from L to R is greater than equal to K, then of course we can have this K. I mean, end of all of these are also greater than equal to K. And if this is for this R, it is less than equal to less than K, then for every R which comes afterwards, it will also be less than K, right? So we can do binary search, but the problem is we don't know how to find, like, what is the end value of the array from L to R. Okay, So how can we find this value? Of course, we could just brute force and just find it using a for loop, but of course there are queries, and queries up to 10 power 5, and it will get time limit exceed. So how we need to find a better way to calculate this and of a subarray. Do you guys have any idea? Or if even if you know sparse table already, it is fine if you want to say it in the chat. Yes. Also, let me, yeah. So we can pre-compute, but how to pre-compute basically? I mean, we could pre-compute a prefix and as well, right? Like as we do for prefix sum, when we need sum of LR, we just like pre-compute the prefix sum, which is like pi is equal to pi minus 1 plus ai. And when we have this prefix sum, we can just say pr minus pl minus 1. So basically we just, if we need the sum of this subarray, we just say get the sum of all of this prefix and just erase or subtract all of these values so that you're just left with these values. But we cannot do the same thing here because this operation does not have a reverse, you can say. I mean, for example, when we are adding, there is minus or subtraction, which is the opposite operation. When we are, let's say, multiplying, there is division. When we are, like, if we need the product of LR, we can do the same thing. We can just say get the product of this prefix and divided by this, the product of this prefix, right? And similarly, if the operation is XOR, its opposite is also XOR. I mean, if we just do it twice, it just cancels it out. So we do the same thing here as well. If we need this, then we do the prefix XOR and just erase these values. I mean, do XOR of this prefix again, and it just erases. And but for example, if it is, if the operation is something like and or maybe GCD, then we do not have anything which can reverse this. Or I mean, how can we, I mean, like if we have some subarray, if we know the answer for this prefix and this prefix, we cannot do any operation between them to like get the value for LR. You can also include min and max because, yes. So they do not have a reverse operation, you can say. So how to do, like how to do them fast? All right. So all we need to do is to find the end of LR for now. I mean, that is the basic problem. Okay. So let me just tell you that we can use sparse table. Of course we can, but the idea for sparse table comes from, like, the idea is very good. I mean, yes. Let me first tell you what sparse table actually does and then explain it. So basically we can have, uh, from every starting point, from every I or L, you can have like you can jump with a power of 2. So basically what we can do is just this. And of all of these subarrays which have the size in powers of 2. So basically the first subarray will just be the size of 1, which is 2 power 0, and then the next will be 2 power 1, the next will be 2 power 2, and so on. So basically what this do, I mean, how is this even helping us? I mean, the computation is of course very nice in this. What you can do is, I mean, the way it helps us is just this, that when you need to compute for example, uh, the AND of 8 elements, you can compute it very easily using the AND of these 4 and these 4. You just have to AND both of these values and it will give you the AND of the whole subarray of length 8, right? So this way, the pre-computation is very easy. Instead of calculating using a for loop over the whole, we are using the other pre-computed values to get the answer. So let me just show you how the code looks like. So basically, we can have something like this, an array of n and log, because for every I we need to store a subarray of length 2 power I, right? And log will be let me just write it here maybe. If for example in this problem, let me just copy and paste the problem again for those who came late. Make prefix sum for bits. uh, Okay, that is actually a good idea, but it will take more time. I mean, when you're querying, you will have to go on every bit, but sparse tables query is better. I mean, it it answers the query in O of one. Okay, I mean, but it was a very good idea that we can have prefix sum on bits. Okay, anyway, for this, for example, the n is 2 into 10 power 5, so we can have log constant integer log as the first power which exceeds uh, like n, because we need to find the subarray, I mean the end of the subarray for each length of 2 power I, but we do not care about those which have length greater than n. So we can have in this case log as 17. I mean, just know that 2 power 17, wait, no, actually 2 power 18 will exceed. You can just do 20 here because 2 power 20 is just, you're sure that it is greater than 10 power 6. Anyways, so I mean, let's not write this, but when we have the array, we can just do this. We can say the first, like the base case, you can say, or whatever this is. I mean, the end of the subarray of length 1 is just a of I, right? And for the next ones, you can do j is less than log j plus plus. So what do we do? Just says sp of I of j is equal to sp of I of j minus 1 and sp of I of actually I plus 2 power j minus 1. right? Because we go to the next, we jump by the 2 power j minus 1 and we go to that element and get the answer for j minus 1 as well. In this way we have computed everything. We can have another condition over here, which is actually over here. If I plus 1 shifted j minus 1 times is greater than n, then you can just say that, okay, what do we do in this case? So if the next one just, I mean, we could put zeros, but we should not put zeros. Okay, so basically all we care about, I mean, in the end, if we have something like this and we want, for example, the end of 8 values, but there are only 6 values, we have computed this for 4. We have not computed this for 4, but we should, right? Yes. So if I plus 1 shifted j minus 1 exceeds n, even then you can just do, wait, yes. Even then you can just do sp of I of j is equal to sp of I of j minus 1. So that even if you computed this, and for 2 power 2, which is 4, you have to go to something beyond the array, you can still have this, because it is better to, I mean, compute everything. Yes. So this will be it. Wait, let me just put else. Yes. So this is the whole code for sparse table. It is quite easy. We can probably reduce it to one line by doing something. Probably not in this case, maybe. I'm not sure. Okay. Anyways, now that we know how to compute end of LR, we can now just use binary search and find the, and how to actually compute end of LR. Let me actually tell you that, because you might be thinking that now we just start jumping from L with the biggest power and then maybe do the same thing for the next value and keep taking the end of these values until we reach R. But this is O of log of n, and we could do the prefix sum on bits solution as well. It is also O of log, but we can do something better using sparse table. We can do the query in O of 1. So if you have the function for query integer L integer R, you can just find the maximum bit or the log of the length basically. But how do you find the log of the length? You can find it using the, let me find the smaller log. You probably know this function or maybe do not, but okay, built-in CLZ of R minus L plus 1. So basically what does this function do is it 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 is very similar to the pop count function. So pop count, like built-in pop count, returns the number of ones in the binary representation of a number. Like for example, for 5 it just returns 2 because 101 has 2 ones in it, right? Similarly, this function's built in CLZ, it says count leading zeros. I mean, it stands for count leading zeros. And what does this do is it just count the leading zeros. So basically, if you have some number, of course, integers have 31 bits, right? The 32th bit is just a sign bit. We can just ignore it for now. And so there are these bits, and then there is, let's say, our number is 5 again. So basically, it just counts all of these zeros. When we will subtract it from 31, like the number of zeros, what we will get is this actually. So this is also the maximum significant bit, and this is also log, because the maximum significant bit is actually the log, because like for 5 it will be 2, like 2 over 2 is 4 and 2 over 3 becomes greater, right? So you can find maximum significant bit or the log like this as well, and this is very fast because it is a built-in function. I mean, this is off one, everything is off. Okay, now we can just return sp of l of log, like take the jump of log of length log from here and end this with sp of r minus 1 shifted log plus 1 of log. Yes, this will be the answer. So basically, I just say I am using something here as well, because like if I need to find the end of all of these numbers, if I find the end of these numbers and the end of these numbers, I can just end them both and these both values, and it will give me the overall end, right? Because even if I end all of these numbers twice, it does not really matter. Same is the case for minimum or GCD or maximum, whatever these functions are. I mean, these type of functions or as well. The type of functions which, like, even if you add a value twice, they don't really care. Like even if you take minimum with x once and take it twice as well, it does not matter. It just matters that whether x was there or not. So we are using this property as well, and we just say that instead of jumping every time, you can just find the value like this. Like you just compute these two, you have computed these two values, just take the end of these two. Of course, this will cover everything because we are taking the maximum power of 2, which is length, which is less than the length. So of course, it will not leave anything in between, uh, because if it does, then there is this bigger power, which is the multiply 2 of this length, which is actually the log of the overall length. So we will cover everything and we will get the answer like this. And now for the general problem, we can just do the binary search as well and get the best R. Okay. Hope you understood the solution. Let's go to the next problem. And that is all for sparse table. I mean, there are only a few problems on code forces. I will add them in the sheet as well. I mean, I know very few problems on code forces which use sparse table. So let's solve this problem. Edges in MST. This is almost a classic problem. Not really a classic. It's hard, but Okay, so let me first actually tell you what is MST. So remember we did DSU, which was like just keep adding the edges until, I mean, if you can connect, then add the edge. So basically, if you are finding some connected components, then you can add the first edge and add this edge as well. If they are already connected, you do not need to add this edge as well, and so on. So we can use DSU to find MST. But what is MST? MST is a minimum spanning tree. So basically, if you have some graph, a spanning tree on this graph is just a tree which, I mean, a subset of these edges which forms a tree on this graph. I mean, it could be anything. A spanning tree is just any tree on this graph. So basically, you can choose, let's just remove some edges basically. Let's just remove this edge, even this edge. I mean, as long as there is a cycle, we can just keep removing. We can even remove this edge. And there is cycle due to this as well. We can remove this. Now it forms a tree. Maybe I did not do erase properly. I mean, it gives a chain. Okay, let's remove this one. So now it gives you a tree. So basically, this is just a spanning tree of the graph. But what is a minimum spanning tree? So assume there are weights on these edges, like 1, 3, 5, 2. So what we have to do is to find the spanning tree with the minimum sum of weights. Like we have to minimize the sum of WIs. I mean, we have to choose the edges in such a way that when, like the edges of the spanning tree in such a way that their sum is minimum. So for example, if we just remove this one too, let's remove this one. Wait, actually it will not be a tree anymore. Let's say this, I didn't put any value here, so let's say this is 6. So let's say 5 anyway. Let's remove this one too, or maybe just this one. And let's remove this one. Okay, now we have a tree, and the sum of these values is just 25 and 14, 39. So this will be the value of the MST, right? Not the value of the MST, but the value of the ST, like this spanning tree. But we can actually have something smaller as well if we delete them optimally. So of course, it is better to keep the edges with the smaller values, right? So we can just try deleting the bigger ones as long as we can. Let's just delete this 14, delete this 10, delete this 8, but we cannot delete it, so let's let it stay there. And we can delete the next one, which is 7. We can delete the next one, which is 5. We cannot actually, so we go to the next one, which is 3. We can delete it, so we just delete it. What was the value here? Maybe it was 2, I don't know. Okay, so now it was not 2, I think. Okay, I don't know what was the value there. Okay, maybe it was 5, I think. So in the end, we will have a smaller. Of course, we should minimize. To minimize the sum, we should keep the minimum weights, right? So basically, this is the Kruskal's algorithm. All it says is just this, that, and there is a proof as well. Maybe I can tell you right now. So basically, if you have a left side and a right side, and when you are uh, getting the next edge or seeing the next edge, you can just see the next minimum weighted edge which join the current graph with the actual graph. I mean, uh, just consider the first edge with the minimum weight, and actually this is Prim's. Yes. Actually, there are two algorithms to find the MST. Let me actually tell you the first one and the second one. So the first one is just this, that you can keep going in the order of sorted order of W, like the weights, and when you have the when you see a weight, you can just, I mean, since we are going in the order of the weight, it is optimal to add the current edge, right? Because if we can add it, we will add it. And what do I mean by if we can or we cannot is just this, like if it connects to connected components, like initially we are starting with just isolated vertices or like with no edges. When we just see the first edge with weight W, we just add it because we can add it, and we just keep going on like this. If we see some edge which connects already connected vertices, we do not add this. Why? Because we already connected them using the minimum possible weights, which were these two. So every two vertices which are connected are connected using the minimum weight. So this is I mean, it makes sense that it is optimal. I mean, at any point in time when we have added these weights, all we have done is we added it only at that point when we could add it. And I mean, let's say we can, I mean, try to prove this using this. Let's say we saw this edge and we could add it. I mean, these two components were not connected, and we could, for example, I mean, we could just add this edge, but we say let's not add it. Maybe it is not optimal, and then later on when we choose something else to connect them, it will be bad, of course, because we are going in the sorted order. It could also be that it is connecting using some intermediate edges like this, but even this will be bad. Why? Because I can just remove the last edge, for example, the one which was added last, and I can just add this edge, and this will reduce the MST, the cost of the MST, or the sum of the weights, right? Because I am just subtracting the maximum and adding the minimum, right? I mean, even if we have uh, even if we decide not to add this edge right now, and later on we found, like, we connected these two components using some other edges, maybe something like this, and now these two are connected, but I can say that I can remove this edge which was added last, because for example, if the value for this is 5, this is 6, 7, I mean, it can be bigger as well, let's say 10. So basically I can just remove this edge and add this edge 5, and this also leads to the same connectivity or the same connected component, but with the lesser cost. So that is why it is optimal to add the current edge if we can add it. So this is basically the greedy algorithm, and it's called Kruskal's algorithm. And how can we do this? We just do it by using DSU. We just sort the edges with the weight value. Like we sort this vector of pair of integer and pair, and then we can just start putting the edges, like we just start merging u and v. And in merge we can also maybe send w as well if we want to find the cost of the MST. And if we add it, of course, not in the beginning. If they can be added, like if their representative or roots are same, we just return. Otherwise, we merge and we add W. Okay. So this is Kruskal's algorithm. And the second one is also, I mean, the easier to implement is of course Kruskal's, but the other one is actually good to, I mean, it is good to know the algorithm. So basically all it says is you can start from any node. Of course, this node will have some edge, right? So it just says you can add the minimum edge which goes out from this to the set of the other nodes. Like you have all of these nodes, right? And if you just start from any node, let's say 1, and you just consider all of its edges, you just choose the one with the minimum weight. For example, these are big, this is 2, so you just add this edge. And when you add this edge, you bring this node to this side. And you do the same thing again. You consider all of the edges outgoing from this part to the other part, and you just pick the one with the minimum smallest weight, and you can bring the other one to this part again. So basically all it says is that if you have two components, I mean, yes, let's say two components, and there are some weights, there are some edges between them, and when you need to connect them, you can just use the minimum weight. I mean, they're kind of similar, but Kruskal's deal. I mean, it just deals with edges, but in this Prim's algorithm, I mean, it considers nodes. It is adding one by one the nodes and the edges. So yes. So basically, these are just the algorithms for finding MST, and that is all which is there for MST. But we will solve these problems and we will see like other properties of MST as well. So the first problem, which is, let me send the link again, which is just edges in MST. It just says like you have a graph of n vertices and m edges. N is up to 10 to the 5. M is also up to 10 to the 5. And we have weights on each of the edges, and weights are up to 10 to the 6. Okay. So all we need to do is to find for every edge in how many MSTs it appears. Not in how many, but all we care about is whether it appears in none of the MSTs, in at least one, like greater than equal to 1, but not all. So the third is all. Either it appears in none, all, or otherwise it will be at least one, right? So yes, this is the problem. For every edge, we have to tell whether this sedge appears in every MST, none of the MSTs, and at least one of the MSTs. So basically there can be more MSTs. Let us see a test case. Okay. So we have 1, 2, 1, 3. 1, 2, 1, 3, 2, 3, 2, 4, 3, 4, 2, 3, 2, 4, 3, 4. 1, 2, 1, 3 is 101 and 100. Then we have 2, 3, which is 2, 2, 4, which is 2, and 3, 4, which is 1. So yeah, what we can do, I mean, what can be over MST is just, for example, just these three edges. We can remove this one and this one, right? And this gives our MST. Now these three edges are part of this MST, right? And the other two are not. But the thing is, we can have some other MSTs as well. For example, we can remove this edge and this edge. And this is the same cost, which is 103. But now the set of edges are different, right? So yes, the answer is actually the same. It's just this. Like there are only these two MSTs. So we just say that this edge is none of them. So the answer for this is none. For these two, they must be in the MST. So we just say that the answer for these two is any. Or you can say all. I mean, any does not make much sense, but anyway. And then for these two, they can be interchanged. Like in one of the MST, one of them is present. So they are present in at least one. So this is the whole problem. Yes. You can maybe think for some minutes. Okay, only 3 of you are present. If you have any ideas, because this is a very, not very, but it is a difficult problem. So you can say any idea, I mean partial ideas as well. Also, there is no way to brute force here as well, because the number of MSTs can be a lot. Yes. For example, it is a complete graph on even if we just have 5 vertices, it will give a lot of MSTs, even if weights are just a bit different. Yes. So there is no way to brute force. Actually, let me just tell you the first fact. I really wanted someone to say it, but basically when we are at some point, let's say we are doing Kruskal's algorithm. So we have right now this tree, and then next we still haven't added all of these edges, let's say, and all of the other edges less than W have been added. All of these edges have weight greater than equal to W. So see what you can say basically, like if you consider this. Well, let's say, let me make it simpler for you. Let's say you are only considering right now, you're going weight by weight, like you just see all the edges of weight 1, then of weight 2, then of weight 3, and so on. So when you're at some weight W, what can you say if you see some edges of that weight? Let me ask you a different question maybe. So, so is it possible that in one MST you have like um, let's say you have some edges W1 and W2, and in the other you have some other edges. I mean, can this happen that in the first MST you have an edge with W1 and in the other you have W2, and W1 and W2 are not equal? Can this happen? Can you say yes or no in the chat? Okay, so the answer for this is actually no. I mean, your thinking is, I mean, of course, very good. I mean, I would have thought the same thing, but this is wrong. So the thing is, in the first MST, we chose the best route, right? And in the other MST, we cannot choose another route with different weights. So basically, the fact is, I mean, you cannot replace a weight with another weight which is not equal. Why? Because because in the first MST, if you had this weight, that means this was the optimal weight, right? And in the second MST, if you're choosing this weight, then it must be equal. Why? It cannot be less because then it contradicts that our MST, our first MST was MST at all. Because if we could choose something lesser, I mean, if W2 is less than W1, that means MST, the cost of the second MST is less than the first one. So this cannot happen. And similarly, the other way cannot happen as well. If this is the case, then the first MST is smaller than the second MST. So then this is not the MST at all. Since they are both MSTs, their total sum of cost is equal. So if we are just changing one edge, then they must be equal. Now, as you say, I mean, your argument could still be something similar, as you have said, that uh, like if there was this route you chose first, but maybe now you can have some other route. I don't know. This, I mean, when there is a cycle, basically, or maybe there are some more cycles, let's say. So basically, in this one, you can choose any route. Let's say our first MST chooses this route, but then I mean, at every point, this was the smallest weight we could pick. So let me actually give them weights maybe. But creating a test case is hard. Of course, I mean, it is true that we have like only they need to be equal, but let me maybe try to show it. Or maybe the first test case was actually good, I think. Yes. So in this one, as you can see, only the ones with weight 2 can interchange. So what is going on is basically, of course, we have to delete 2 edges, right? And we most definitely delete the 101 because it is too large and it is also part of a cycle. So we just delete it. Then we see the next cycle, but we cannot delete 1 because it is too good. And in 2's we have choice. So in the maximum one, in a cycle, when we have actually a cycle, we can just say we can delete any of those edges which have the maximum weight. So basically, this is a very good fact. Or the smaller fact is just this, that only uh, equal weighted edges can be like interchanged from one MST to another MST. And the other fact is, when you have a cycle, this happens. So basically, these two are really good facts. And the fact that it will only change when we have this W, basically, I mean, what I'm trying to say is this: if we are going from W equal to 1 to 2 and so on, what is actually happening is, at every W, we right now we have the best possible connected MSTs, or the MS forest, whatever it is right now. So basically, without these edges, I mean, right now, till we, I mean, let me just erase everything. So if we have added every edge in the order, and I mean using Kruskal, every edge which is less than W and in the order, and it has given us some components. I'm just claiming that this is the best we could have, and we cannot interchange any edges. But when we see the next, like the edge is equal to W right now, all we have to do is to put some of these edges so that they, or maybe, I mean, let's not connect everything. Maybe it is just like this. Okay. So even in this, we have some choices, right? I mean, all we can do is maybe pick this one, and this one, and then we this will be, I mean, joining the same component, and we do not really need to put it. But the thing is, there is a choice. I mean, I can just instead of placing this, I could just place the other one, like this one, and now it is still connecting the same components. But as the, I mean, the main algorithm of Kruskal or Prims, you can just use the same argument, or we used while proving the solutions, the algorithms, that we have to do, I mean, we have to, if this W is actually connecting these 4 components, then we have to connect these 4 right now using the edges with this weight. Why? Because if we do it with a greater weight, of course it is unoptimal, and we could not do it with a lesser weight. Otherwise we would have done it, right? So this is the, like, the greedy idea in this MST problem, that when you are at some W, you have to add all of those edges which are connecting the components, right? And in those, you can have choice when you have some kind of cycle. That is the whole problem, basically. For example, like this. In this, what is going on? Basically, we will start from the first edge, the minimum weighted edge, which is from 3 to 4 with weight 1. We said, okay, this is very nice. But the next one, there are two edges with same weight, we say we have to put one of them. We have choice in both, so the answer for both will be at least one. For this one, we didn't have any choice, so the answer for this is all or any, like it is in all MSTs. But for these two, the answer will be at least one. And for the next one, which is 100, we just say, okay, there is no choice, so we have to put this, and it will be in all as well. But for the next one, it is connecting the same component, so the answer for this will be none, because it is just joining the same components, so it can never help us, right? So basically, all you have to do is this. When you are at the current W, you consider all of those edges with this weight, and what you need to do is to say, is this edge a part of the cycle or not? If this edge is part of the cycle, then the answer for this is at least one. The implementation is actually quite hard for this. I mean, it is hard, but I think my solution was not bad. You can maybe see my code later. But if it is part of a cycle, the answer will be at least one. I mean, the answer for all three of these will be at least one. Let's just say greater than equal to one. But for this one, which is not part of the cycle, the answer will be all, because it has to be added no matter what. Because if we do not add it right now, we will connect these two components with the verse weight. Okay. So if you guys are, I mean, saying something, the solution, then you can just tell me. Okay, then we are, yes. Thanks for answering. Okay, I have now explained the solution, so okay. So do you guys understand the solution? If there is any question, you can just ask right now. And for those who came a bit late, maybe they can see the recording. We were discussing MST, and we discussed the algorithms to find the minimum spanning tree, and we also discussed this problem, which is edges in MST. Okay, so let's move to the next problem if you guys don't have any questions. So basically, I mean, you can see this was a hard problem, but the hard part is, I mean, it is not that hard, right? It is very logical. I mean, you can solve it. You guys have potential, and you guys can solve all of these problems. Okay, let's move to this problem. I've sent the link in the chat. The problem is just this, that you have a connected graph, of course, and for each edge you just have to say what is, I mean, you let me just maybe write the constraints. Nm is 2 into 10 power 5. You're given a graph, there are n nodes and m edges. And all you have to do is to find for each edge, I mean, for each edge, you just say that you have to include this edge now, and find the spanning tree which includes this edge and has the overall minimum weight. Maybe let's just see the test case. Okay. 1, 2, 1, 3 with weight 1 with weight 3. 1, 4, 2, 3, 1, 4, 2, 3. Okay, this is getting complicated. Let's add 4 here with a weight of 5 and 2, 3 with a weight of 2. Then we have 2, 5, 3, 4, 4, 5. So we have 3, 4, 4, 5 and 2, 5. 4, 5 is 4 and 2, 5 is 3. Okay. So for each edge we have to answer what is the minimum spanning tree value, but this edge must be in the MST. I mean, this is very easy if M had been very less. Like if M is okay, let me actually just ask you this, because of course we are going to participate in the Olympiad, so we need to solve for subtasks. So let's just say M is up to 10 power 3. You can also say M is less than M equal to 10 power 3. How will you solve this problem? Maybe I can explain the answers for the test case. For example, for the first edge to be in the MST, this is always in the MST, of course, so you can just pick it. Then you can pick this, this, and pick this. So the cost will be 3 plus 1 plus 2, which is 4 and 6 and 9. Yes, the answer is 9. Like for this edge to be in the MST, the answer is 9. But of course the overall MST is different. It will be just this, this, this and this, and the cost is 1 plus 2 plus 2 plus 3, which is 8. So of course the MST will now be different if we are including some other edge. Okay, let me see if you guys have any solutions. Okay, so you can think generally as well, but if you have any solution with these constraints, let me know. Or if you have any observation or idea, let me know that as well. Okay, guys, I want you to first focus on the subtask. So if you have the solution, just tell me that too. Okay, guys, let me first tell you the solution for this. So, as you know, the MST algorithm is just this, that you have all of the weights or the all of the edges sorted by their weights, right? Like the minimum weight comes first. For example, for this, uh, all of the edges come in this order, in order of their weights, right? And then we just add them. What we can do if we have less edges, we can just, to make sure that we add the first edge or the edge we want to add, I mean, which is the must to add, like the, if we are finding the answer for the ith one, then we can change our order. We can just put this edge in the very beginning so that it is always added. I mean, this is how our algorithm works, right? We just say that if we have to like, this edge will only be added if it connects to two components which are not connected, right? So basically, if we just put this edge in the very beginning, then it will always be added, and we can just put the rest of the edges in the sorted order. So we just have to put the like remove the ith edge from this place and just put it in the beginning, and then we can do the same algorithm again on this order of the edges and find the MST. That will give us the MST, which will have this edge as well. I mean, it will have this edge and the overall minimum cost. Okay. And some of you mentioned, I mean, the ideas for complete solutions. And in those, I mean, I found some similarities. So maybe I should tell you that, for example, if you have these nodes, and for example, you are trying to find the answer for this edge. Okay. So, and let's say the values are 1, 1, 2, 2. So for this one, when you have to find the answer for this edge, the answer will be just this, right? So even if the MST you first found was this MST, the one with let me draw again maybe. So let's say you found this MST 1, 2, 1. There is this extra edge with weight 2, and then if you are finding the answer for this one, for this edge, then you can find the answer, I mean, with by deleting this one instead of deleting any of those which are directly connected to U or V. So some of your solutions had this idea that if you're adding this, then you can delete one of the edge from U or V, but that will make it unoptimal. Okay, so basically what we can do is similar to the previous problem. I mean, okay, so if you have an MST, of course it is a tree, right? So say you have this tree. Let's say you're finding the answer for this edge, which is extra. Of course, the answer for those edges which are in this MST are just the value of the MST, right? Because they are part of this MST, so uh, that is all. That was like the condition of the problem. If this edge must be part of the MST, what is the cost of that MST? So for all of these edges, the answer will just be the the actual MST's cost. But let's say you are now trying to find the answer for the edge which is not in the MST, for example, the edge between these two vertices, U and V. So what can you do here? I mean, which edges can you delete so that this tree stays a tree? Okay, so for this edge to be added, which edge can we delete from the tree so that this is added and it forms a tree again? We can delete any edge which is on the path from U to V, right? Like any of this, sorry, this, or this, right? Why? Because of course, if all we care about is, I mean, having unique paths so that it remains a tree, right? So we just need to make sure that if we delete any one of these edges, for example this one, then it will remain a tree, right? Because now I mean, what happens is when you delete one edge, a tree just becomes two components, right? So when you are adding this edge, you must delete some edge which, I mean, separates them in two components such that uh, u is in one component and v is in the other one. So you can do this by removing some edge on the path from u to v. So for example, if you remove any other edge which is not in the path, of course it will not work. I mean, if it is below u, it will not work. If it is below v, it will not work. If it is not in the path, for example, you delete this edge, then u and v will still remain in the same one. So to actually put them in separate components, you have to delete some edge which is on the path, right? So what is now what is left? I mean, if we are adding this weight, which edge should we remove so that it is MST? Of course, it will be on the path from U to V, but which one specifically? I mean, I will just assume that you guys are not answering, but you guys know it. I mean, this is easier. So uh, we will just delete the maximum weighted edge on the path from U to V, right? Because if we are adding any edge, we don't care the weight for this one. All we care about is we have to maintain a tree and we have to make it a minimum spanning tree. So to make it the minimum, if we have to add this edge and we can only delete one of these edges, and to have the minimum cost overall, we will delete the maximum weighted edge, right? The one which has the heaviest, which is the heaviest edge in this path from U to V. So the one with the maximum W in the path from U to V. And how can we find the maximum weight of an edge from like U to V? Do you guys know? Or I mean, yeah, of course, thinking. I mean, I'm not asking you to think, but if you already know, you can tell me. Like how to find the maximum weighted edge on the path from U to V. Okay, I guess you guys don't know. And it's fine because we are going to learn it. We will use LCA. Now what we have to do is to find, okay, no, we cannot do that. Okay, so what we have to do is we have to find the LCA like this, and then take the maximum overall as well. So that is why I first taught you sparse table, because these topics are very much related to each other. So what is LCA basically? LCA is just the least common ancestor of two vertices. So for example, I mean, let's say there are two vertices u and v. This needs not to be the root, but anyway. So for example, this is our whole tree, something like this. There can be more vertices. And we just want to find the least common ancestor of u and v. What is the least common ancestor? It is the first vertex on the path from u to the root. That, I mean, the first ancestor which contains both u and v. For example, this ancestor of u is not an ancestor of v, right? So this is not a common ancestor. But if you go one step above, then you see this is a common ancestor and this is the least one as well. I mean, this is the closest one as well. Of course, the root is of course the common ancestor for everyone, but we are finding the first common ancestor. So this is LCA. Of course, we can find it using naively using brute force. We can. So what will be the algorithm to find LCA using brute force? So basically, first we need to make sure that they are on the same height. So we just go from v to the height of u using, of course, one steps. Like we just say v is equal to parent of v, and do this while height of v is greater than height of u. Okay. So when you do this, it will reach here. And now you can just say while v is not equal to u, you can just say v is equal to parent of v and u is equal to parent of u, right? This way you are moving up one step from there and one step from there, and you keep doing this until you finally reach the LCA. Okay, this is how you can find LCA in O of n, because this is taking O of n steps, right? I mean, height can be O of n. So we need to do this faster, of course. How can we do it faster? Probably you guys don't know about square root approaches. Maybe we can discuss that as well. So we can store, instead of just storing parent of v, we can store parent of v of sqrt. Like have this array, and sqrt is around like square root of n. For example, n is 10 power 5, then, or maybe let's say 2 into 10 power 5. Let's just say let's just say 10 power 5. So then square root will be something like 310. So you can just have this array, and you can just say when you have to do these operations, you can do them faster. How? You can just say yes. So to do this, you can just say that you will try to move with the biggest step you can take, which is square root minus 1 or square root, whatever. I mean, we don't care about specifics. We will try to jump by the square root, but if it is crosses this height, you can just jump by height of v minus height of u, right? So this will take n divided by square root steps. I mean, we can even include this and it will still be the same. And when you have reached the same height, like u and v are at the same height, then we can just do, we will again then try to take the maximum step, which is square root minus 1, the jump with the square root minus 1. And if they are equal, then we know that the LCA is close by, like it is less than square root steps. But if it is not equal, like this ancestor, which is the square root ancestor, like square root times, if you go up, the one which is the ancestor, if they are not equal, then you can just move both of them up with that jump, right? But if they are equal, then you can maybe even go naively, like go one by one and see when it becomes equal, because it will just take square root steps when you are very close. So overall, when you are jumping by square root, you just spend n divided by square root steps, and even if you spend square root steps more, this is overall, because n divided by square root of n is just square root of n. So this is in total 2 times square root of n, which is, I mean, O of square root of n. So which is, I mean, a very good idea. Okay. So you might not have seen many square root approaches, but square root solutions are very nice as well, because sometimes they are very easy to implement, and I mean, it does not use uh, like more ideas or more observations, because you can optimize using just the square root. Okay. But now we have an algorithm with like log of n, so of course we will do that. So how can we find the LCA? We can find it by jumping by powers of 2. I mean, this idea is so good. I mean, it is used in so many problems and so many algorithms as well, as you can see. There are some other problems which are very hard, even IOI problems, which use these type of ideas, like jumping or doing something based on powers of 2. They help us a lot, and even they help us in representing in binary and so on. So yeah, how can we do this using jumping by powers of 2? We can do the same thing. We can have parent of n of log, like just store the parent which is 2 power I steps ahead. So of course, for parent of v of 0 is just, let me actually write the code. Okay. So parent of v of 0 will just be, maybe I can start from the DFS. I mean, what you do in the DFS is integer, you're on integer v. And when you go on the neighbors, in g of v, you can just say this. Of course, there will be a p over here. Actually, you don't need this when you are already storing the parents. So if u is parent of v of 0, which is already defined, you can just say continue. Otherwise, u is a child, so you can say parent of u of 0 is v. You can define its parent. You can also define its height. Height of u is height of v plus 1. and then you can, let me actually write this here, and then you can just iterate on, let's maybe name it J because we are jumping, J++, and you just say parent of I of J is parent of what? It will be parent of I of J minus 1 of J minus 1. So basically this is the same idea. So when you have to find the ancestor which is 2 power j steps ahead, you can find the ancestor which is 2 power j minus 1 steps ahead, and then find the one which is 2 power j minus 1 steps ahead of that one, because of course if you add these two, it gives you 2 power j. So this is the fact we are always using to find it. And you can maybe define, yes, you can probably define parent of the root of j as the root, so that it does not go, I mean, or maybe if even if it is 0, then everything just goes to 0 back again. I mean, when you're doing this and it goes like it exceeds the length, let's just say you only have 2 parents. So for this it will be parent of u of 0 will be this, parent of u of 1 will be this, but parent of u of 2 should, I mean, you can define it any way you like. You can either define it like this, that root is the parent of itself, or you can define the root's parent is 0, an imaginary node, and then of course everything in the array will be 0, so zeros, even jth parent will stay 0. Okay. Anyways, so when you have all of this, it is, I think, better to define parent of root of j as root. It will help us and avoids unnecessary conditions. And then we are when you are trying to find LCA, how can you do it? Actually, we will just use the brute force ideas. Let me see if you guys okay. We will just use the brute force idea that you have to first get them on the same height and then move from there, because if they are not at the same height, we cannot really compare. So this is, I mean, it is must to have them at the same height. Okay, so when you are finding the LCA of u and v, you just do this. First you can say, to avoid unnecessary cases on conditions, you can just say if height of u is greater than height of v, then swap uv, so that you know that the height of v is greater, so you have to move v up towards u, right? So you just say that you have to travel by d, like this is the distance between the heights, or the difference between the heights, so you just have to travel by this much. So I just say that since you have to travel by this difference, you will just take, since I can just take the jumps with power of 2, I will just say I will go in the binary representation of this difference. Let's say I have to travel like 10 steps, which is, or maybe 11, let's say, which is 1011. What I will do is just go on these, go on the binary and see is this one on? Yes, it is. So I just say I will move by this. I will take a jump by this, like by 2 power 1, or actually it is 0, so 2 power 0. And then I will take a jump from of 2 power 1 as well. And this way, of course, since this is the binary and I am jumping with each one, this will take off log time because there are log bits, and of course I will cover the d distance because I have gone by like 2 power 3 plus 2 power 1 plus 2 power 0, which is 11. I mean, of course, I used the binary, so I could not have done it wrong. Okay. So now u and v are at the same height. I can say if height of u is, of course, they are on the same height. If u is v, you can just return right now. Otherwise, what can you do is you just try to pick the largest step you can take. You just try to take the largest step you can take. If they have, I mean, of course, they will have the same heighted parents. If they have the same same ancestors, then you cannot like make them equal, right? Because the lowest and common ancestor could be lower than that, right? For example, let me extend it from here. So if the largest, okay, let me actually press this one, right? If the largest step is, for example, this, and okay, basically u was below, then of course LCA, this is greater than LCA, right? But we do not want to go there. We will take the largest step we take such that they are still not equal, like something like this. And we keep doing this. We take the largest step that they are still not equal, and so on. So what do you think? I mean, will this work or not? Of course, we will never reach the LCA of u and v, but where will we be if we just do this? And let me write the code for you. We will just start from the biggest power of 2 and we will come down to 0. And then we can just say if parent of v of I is not equal to parent of u of I, if we take this jump using this power, and if the parents are not equal, then you can go there. Okay. And now we have to return something. So my question is, I mean, this is very hard, so let me just tell you. So basically, I always jump when they are not equal, right? If I had jumped from the bigger power, like just the bigger power from here, like the multiply 2 of this jump, then I would have reached the common ancestor. So I said I will not take that jump. I will go little by little. Maybe the common ancestor is a bit below it. And I will just keep going. Maybe this goes there, but I will not take that jump. I will instead take the smaller one and go here and here. And I'm just closing the distance. So at the end, I actually claim that at the end, I will be at the, like u and v will both be the children of the LCA. Or if this is LCA and these were u and v at the same height, and when I do this, like I just jump whenever they are not equal, I will at the end reach the two vertices which are like just below the LCA. So I can just return parent of any of them, the immediate parent. Why can we say this? Actually, this is a bit hard to explain for me, but I will try my best. So basically, let's consider the distance from LCA to U or V. I mean, they are at the same height now, so it does not matter. So the difference between them is of course just the height, right? So let's say the difference is D, but I am claiming that we are moving by, or we at the end we have like covered the distance D minus 1. And this is true. Why? Even though we do not even directly know what is D, we are still doing the same thing. I mean, we are covering this distance. Why? Because I take the biggest jump whenever they are not equal. So what does this mean is, I mean, if I had to like take the, I mean, if I had to just go to this node, which is D minus 1 steps apart, I will, I would have done the same thing, right? I mean, not the same thing. I would have known the distance. So I will just go on the binary representation and I will just say, okay, if this is 1, just take this step. And I would have taken these steps, right? But now that I don't even know this value, I can I can still do the same thing, but my condition is like these two should not be equal. So this will work because I mean this way we are doing the same thing, like uh, like this is the maximum we can reach, and we will reach it because we are starting from the maximum power and we are saying if they are not equal, I will take this power, and this way it will exactly reach d minus 1 because this is the maximum one where they are not equal, like the ancestor of u and the ancestor of v. So I hope, I mean, even if it is not that clear, like how is this working, it does not really matter. I mean, this is just for the proof. So you can just assume maybe this always work, or maybe you can read some article which is explaining the proof in a better way. But I mean, I hope the intuition is clear that we are jumping by the maximum power when they are not equal, and this way we will at the end reach the maximum point where they are not equal and which will be the immediate children of LCA. And when we will return the parent, we will be returning the LCA itself. Okay. So this is LCA, and for the original problem, now we have to actually make some changes to the LCA. So when we are jumping, we should not only just jump, we should also take care of the maximum. So in this code, we will make some changes, like we will keep track of maximum as well. So what exactly we will keep track of? It will be max of u of 0 is w, and w is of course from this edge, like auto w u g of v. I mean, in V, we have stored the pair, which is U and W, like the whole edge with the weight. And then we can say that U of 0 is like if you just take the first step, what is the maximum uh, weight? Of course, there is just one edge, so maximum is the same thing. Otherwise, we can do the same thing here. I mean, almost the same thing. max of I of j will be maximum of I of j minus 1. Like what is the maximum of weight on the edges in the first 2 power j minus 1 edges, right? And maximum of, okay, let me just go to the next line maybe. Okay, maximum of parent of I of j minus 1, because I have to first move to the move by 2 power j minus 1 steps, and then I just take the 2 power j minus 1 edges from there, and the maximum of these two is the maximum of 2 power j edges from here, right? So this is it. When I have this, I have everything almost. And when I am finding LCA, I can just find the answer as well. I can just say answer will be, write it here, I guess. Answer is equal to maximum of answer and maximum of V of I. So you are moving from V with 2 power I steps. So you just say what is the maximum on 2 power I edges from here, right? And similarly from this part, these two parts, let me actually put the bracket now. Okay, I can just say answer will be maximum of answer and max of V of I, because we are moving from V with step of I, and answer is maximum of answer and maximum of U of I. Actually, we have to do this before moving, so we will write that here, and that's it. And we can return the answer now, because we don't really care about the LCA. We only care about the maximum weight on the path. But actually we have not accounted for the last two edges, which are closer to the LCA. So we will have to do answer is maximum of answer and max of U of 0, and answer is maximum of answer and max of U of 0. Yes. Now when we return answer, it will give us the maximum weighted edge, which is on the path from U to V. Okay, I mean, this was a bit hard, but of course we have to cover this because this is actually, I mean, not hard, not easy, a medium topic for IOI. But I mean, of course, for bronze, this is a hard topic. So yes. So if you have any questions, just let me know. You guys don't speak a lot, I guess. Have you guys understood everything? I hope. Okay. So yes, I mean, this is not hard, but of course, it is hard to come up with when you're thinking on your own. Okay, great. Let me see what was the next problem I had to. I was thinking that we will maybe solve some extra problems but now is a bit late for that. Let's solve this problem. Blood cousins. Forgot the problem, so maybe I have to read it. Okay. So we have some queries and we have a tree on n vertices, and we are given queries, M queries or Q queries, which are also up to 10.5. In each query, we are given a V and let's say a D. So what we have to do is to say how many vertices are there which are like the dth cousins of V. And what do we mean by the dth cousins is just this, that all U's which are like, if I have this parent at distance D, like the dth ancestor, all those vertices who also have this as the dth ancestor are my dth cousins. So basically, my first cousins are actually my siblings, or the ones which have the common parent with me. The second cousins, or if this is 2, then they will be those vertices which are like here. Yes, these will not be counted now because they are my first cousins. So these will be my second cousins. If there are more vertices, then yes, something like this. So all of these will be my second cousins, and so on. So all I have to answer is this, that how many dth cousins this vertex has. Actually, and before that, I mean, I used it, but I'm not sure if this problem actually requires it or not. So let me actually tell you another concept. We have to cover everything. So yes, it is called Euler tour. It is a bit hard concept probably, but still bronze level. Okay. Actually, I remember a problem which is IOI problem which is solved using this, and it is a very easy problem. So the concept is just this: when you're doing a DFS on a tree, you just put the number on the vertex, like the current number, like you just renumber the vertices, for example. So you just put 1 over here, 2 over here, 3 over here, 4 over here, 5 over here. Then you go to this vertex, so you put 6. Then you go to this, 7, 8, 9, 10. I mean, you just label the vertices in the DFS order. This is called Euler tour, and it has many other definitions. So this way you will just number the vertices, right? Okay. So this is, I call this like the starting time. So what I mean by this is you just set the starting time of this vertex as the time at which you came in the DFS on this vertex. So when you do DFS on U, you just say st of u is equal to current time, or the current variable, whatever you name it, current time plus plus. I mean, you can do current time and then do current time plus plus, but I just write in one line most of the time. Okay. And then you're doing the whole DFS thing. Okay. And this way all of these times are assigned, right? This is just a number you're assigning, but this is very useful. Also, you can similarly assign another number, which is the end time. End time of V is equal to the current time. That's it. No addition in this. Why? I mean, what are we assigning the end times as? This tree is too big, but let's just try. Okay. So basically, we will have 5 over here because end time remains the same. When you are then you will go to this vertex, and then you will say the time is 6 right now, so you will put a 6 here when you will go out. And when you will reach here, the time is 6, so you just say then time for this is 6, and so on. This way, I mean, it is like the maximum on the sub in the subtree, right? The maximum starting time in the subtree, something like that. So basically, of course, it is in our case, it is just coming from the right side because that is the last guy we visited. And similarly, you can fill the whole tree to this side as well. Oh, sorry, this will be 14, this will be 15, this will be 15 as well. Then you go to 16, you have 17 here. Then you go to 18 and 19, you have 19 here, you have 20 here, you have 20 here, you have 20 here, and you will have 20 here. So there are many good things about these numbers. First of all, the starting times are forming a permutation, right? Because they are from 1 to n. This is the first property, you can say. The second property is a very good property, that like if you want to find whether u is in the subtree of v or not, now you can do it very easily. How? You can just say if u's starting time is between v's starting and ending time, like if st of u is between st of v and it is, wait, yes, it needs to be less than equal to n time of v. Yes, right, less than equal to, right? Yes, because for example for this it is 15, and if I'm finding for this, then it needs to be less than equal to, yes. Okay, now you can just have this one line condition and it just tells you whether u is in the subtree of v or not. So this is a very good thing. Another thing which is very helpful is that the sub tree of a node have consecutive numbers. So when you list all of these, like for example, if you take any subtree like this one, the numbers are 12, 13, 14, and 15. For this one, the numbers are 3, 4, 5, 6, 7, 8, right? So this thing is very good as well. Actually, how this helps us is a bit, I mean, it's a bit advanced topic, but not really. I mean, now we can just form this tree as an array, right? Like we can just put the first, the one with the first starting time as the first node, let's say, and so on. This way, a subtree becomes a subarray because we said they have consecutive numbers, right? So from 3 to 4, 5, 6, 7, 8, like all of these are in one sub, like this subtree is now forming a subarray. So this is a very good property, because when you will have to perform some operations like add in this subtree or subtract in this subtree and so on, you can now think of it as like performing the operation on this subarray, because you can just form this subarray and then you can just say if I have to perform the operation on the subtree of 3, I will just perform the operation on st of I mean the node is something else actually, but its starting time is 3 to 8, right? So you will just do it from the starting time to the ending time of that node, and that is its subarray, and you can just add or subtract in that subarray. So this is, I mean, this is very good thing, because I mean, you are now forming the tree into an array, and you can do operations on that array instead of on a tree. Okay, but yes, so for this problem you only need, of course you don't need to perform operations or anything, so you only need, I mean, you might not even use them at all, but I use them. So anyway, I just thought that you should know this. You should know this, like the starting times and ending times. They help in a lot of problems, which are mostly like data structure problems. But anyways, okay. So you can think on the problem for a bit. Like you have to find for V all of the, let's say, let's call this ancestor A, all of the nodes which are like dth cousins, and they should be exactly be dth cousins, not like d minus 1. Of course there might be some nodes like this, but they will not be counted because they are not the dth cousins. We need exactly dth, something like this or something like this. All of these are dth cousins. Okay. Actually, this is a very hard problem. I do not really expect you to solve this in a very limited time. and we have, and over is even less. So I will just tell you the solution now. Okay. But I do not really want to. I guess it's fine. I mean, you should really try to solve the problems I have added in the sheet. They are very good. I mean, some of them are really, really good. Like they are very important for you to solve and think on them, because like they will develop or they have such new ideas that if you discover them by yourself, it will be very nice. Okay. Maybe I will put some star or something like that on the very important problems on which I think you should think on. So you can maybe prioritize them. Anyways, but most of them are going to be hard. Yeah. Okay. So what we can do here is we can just renumber the vertices. As I said, we can just, I mean, as I told you guys, like we can just, instead of having the real numbers on the, or the vertices with the real numbers, like if they have given us, for example, 3 here, 5 here, 7 here, I don't know, something like this, I will just renumber them according to the starting times, like as in the DFS order. Okay, now that I have them in that order, I can first do this, that I will just find this ancestor which is at the dth height, of course using the parent of n of log. Like we can just jump with that, like just jump that distance using the powers of 2. And then what you have to do is to find all of the vertices which are in its level and are like at this height, right? Like at the d plus height of a, right? You just have to find all of these vertices which are in its subtree and at this height. So what you can do is put, I mean, there could be more vertices at this height, right? Like something like this. It's a bit hard to draw, but you can imagine, I hope. But you only care about these vertices which are in this subtree. Okay, so you can just add, you can just have some level, like vector of level, and at each height, like level of height of u, you push back u, like you just store, and u is not the u, like the actual u, it is the starting time, because all you care about is the starting time now. You just have relabeled the vertices, you can say. Or maybe if you have not done that, you can just write st of u here, whatever you prefer. Okay, so height of u dot pushback st of u, or u if you have put the starting times now. Okay, so now we have, for each level we have the starting times, right? We can sort each level based on the starting times, and now we know that all of these will be consecutive, right? This is again the property of the starting times, because all of these are smaller ones, because we first go to them and then come here, and then after all of after visiting all of these in this ancestor, and then we go to the right side. So all of these will be consecutive. And now I can binary search on this level and find the first node which is in the subtree of A, or not in the subtree, because this is not monotonic. These are not in the subtree, these are in the subtree, but these are not. So we cannot do binary search like this. like with this definition, but we can do it like find the first node with the starting time greater than the starting time of this. Actually, this is just a lower bound, I think. Like you just find the first value which is greater than equal to st of a in this level, right? So you first find this node, like the index of this node, and then you find the last node, or you can just find the first node which have greater than uh, like st, like the starting time greater than the ending time of a, right, using upper bound. And you can just now you just have all of these nodes, right? But all you wanted was the dth cousins, not the d minus 1, d minus 2, and so on. Not those. You have even counting the zeroth one, v itself, which we do not really, count, which we do not want to count. So to subtract them, we can do the same thing, but for the ancestor which is just below. And this will count all of the vertices, but all of the cousins or siblings or whatever from 0 to d minus 1. So it will, we can just subtract all of those which are not like uh, which we do not want to count, of course, like the zeroth cousins, first cousin, second, and so on till d minus 1. And this way we will have the only dth cousins. I mean, this is a bit hard problem, but as you can see, it just uses basic concepts, not anything really hard. But this is 2200, I think. Okay, it is 2100. Okay, so I'm a bit tired, but maybe we can solve another problem. I do not really want to spoil the very good problems. Let me actually first tell you. Okay, so maybe there is a message in the chat. Okay, somewhat correct. Okay. So yeah, let me actually send you the problem links right now. Maybe you can think on them right now if you want to. Like if you have any idea, you can just tell me. I actually wanted to solve this problem in the session, but given the time, I do not really want to, because I really want you guys to think on it by yourself. Actually, you guys probably don't know some some things which will be used in this problem. So first, let me tell you that as well. And probably I will not get time in the next sessions to explain you those things. I mean, they are very good concepts, but they are, I mean, not like very classic concepts. So I will just discuss probably one of them. It is called diameter of the tree. And this is well known. I mean, it is not like it only appears in code forces or anything. There are Olympiad problems. Is there any IOI problem which has diameter? Probably yes. I think I have seen it. Oh, actually, in 2025 there was. Yes. Okay, so what is the diameter of the tree? Diameter of the tree is the maximum distance between two vertices in the tree. So for example, maybe let me make a better case, because sometimes people just, or even I myself, just think that the diameter will be something like from there to there, like passing from the root, but it is not really the case. It can be something like this. Okay, so the diameter of the tree is the maximum distance between two nodes in the tree. Maybe in this one it can also be this, but maybe we can extend it further and make it impossible. Okay. So now the diameter is of course this. Let me actually, instead of drawing each node, let me just draw this. You can assume there are a lot of nodes here. There are only a few nodes here, and there are some nodes, let's say here, some small subtrees. Okay, so let's say the diameter is this. I mean, you can see that this is probably the farthest distance. If it is not, then you can extend it probably like this. Anyways, so the diameter is the farthest distance from of two nodes in a tree. How can you find the diameter? Do any of you know? Like, how can we find the diameter? First, if you know, you can put a plus or a yes, and then tell me using my code chat, like, how can you do this? Okay. Yes, you're right. Nice. So, actually, the first fact is, I mean, the facts are really good for the diameter. I really like the facts. So basically, the algorithm is, the first algorithm is this. There are probably two solutions to find the diameter. Okay, the first solution is this. You can first start from any node, let's say start from 1, and just find the maximum node, like the node with the maximum distance. Of course, you can find the node with the maximum height. Since it's a tree, you can even do a DFS, but if you want, you can do the DFS as well to find the maximum distance. Now you know the distance is from 1. So you just get the maximum, you just get the node with the maximum distance from 1. Now you do another DFS from that node, the one which is farthest to V. Let's say it is V, and V is something like, so this. And then you do a DFS from V, and you find the farthest node from V. Let's say it is something like this. Okay. And this way you will have the diameter. Of course, there are some things which are not like proven, you can say. So the only thing which you need to prove prove that your solution is correct. Of course, this solution is correct, but why is it correct? Because if we can just prove that V was one of the nodes of the diameter, then it is of course correct, right? Because if you find the farthest node from one of the nodes of the diameter, of course it will give you the diameter like the other node as well, which forms the diameter. So all you have to do is to prove that the farthest node from 1 is one of the diameter nodes. Actually, this will be a bit higher than V, because otherwise we would have first find Q and then find V. Anyways, okay. So all we have to prove is that the farthest node from any node is one of the diameter nodes, because we can pick any node instead of one. So anyways, let's just pick one. Okay. Actually, the first fact or the first observation is just this, that you and we will be leaves, right? Of course. I mean, if they are not, then you can just go down, further down, and extend the diameter. Of course, and that will bring you a contradiction. Okay, so if we have, I mean, we can prove everything with the contradiction anyway, but let's say the diameter is V to U, so it is something like this, let's say. So the path from 1 to V, I am claiming that V must be the one of the nodes of the diameter, right? I don't really know how to prove this. Can I prove this? Yes, I can. Okay. So we can actually prove this using contradiction, and we can say that, like, let's say there was some other diameter instead of U and V. Let's say it was X and Y. There are a lot of cases actually in this one. Okay, but anyways, let's just say it looks something like this. So what you can say here is, actually you can bring a contradiction here using some inequalities. For example, first you can say that this distance, let's call it d1. There will be a lot of d1, d2. Okay, this is greater than equal to d2. Why? Because v is farthest from 1. So d1 is greater than equal to d2. Of course, this was like a common point. And then similarly, you can say that this distance is less than equal to this distance. Why? Because when I find the farthest node from V, it gives me U. It would have given me X if this was larger than this, right? So we can say, let's call this D3, D4. So I say D4 is greater than equal to, or maybe let's call it D3. Okay, so D3 is greater than equal to D4. So yes, this proves everything. Like, since, I mean, this brings a contradiction that xy is not the diameter. I mean, even if it is, then uv is also a diameter, because this was a common path in xy and uv. This remains the same. But for the other paths which are not common, the bigger one is actually the one which contains uv, right? So this way we can bring a contradiction using what we have done actually. Like, the only two things we have done is, like, v is the farthest node from 1 and u is the farthest node from v. And this way we have, like, proven everything. And we can probably prove the fact that from 1 the farthest node is part of the diameter. Because if it is not the part of the diameter, let's say the diameter is something else, let's say it's x and y, and we found b, we can probably, I mean, have the same logic. we can have something like this. This is less than equal to this, and we can say since this is less than equal to this, we could have a larger length with Vy instead of Xy, right? So this is obvious as well. And what if it does not even have intersection? What would that mean? Something like 1 to V, and let's say X and Y are like here. Okay. Even in this case, as you can see, it is better for one of them to actually go to V, right? Because the farthest distance from one is to V instead of to X or anything. So instead of like having this distance, which is so less, you can instead go to 1 and then to V, right? So yes, I mean, if you consider all of these cases, whether there is overlap, there is no overlap, in every case you will find out that uh, this algorithm works. Of course it works. Okay, let me actually tell you the other solution as well. It is using dynamic programming. Actually, I have not taught you dynamic programming, but probably you guys already know. We will have uh, some problems probably in the next session of dynamic programming. Okay, so what we can do is keep track of two things. I mean, DP is also very intuitive. It just feels hard and scary, but it is not. I mean, if I have not told you like it is, we will use DP, probably it will be easier for you. Okay. So all we need to do is for each node, find two maximums. What maximums we will find? The maximum depths of two nodes for each node. So for this one, of course, it is itself the maximum, and there is no other node below it. For this one, you can keep track of two of its children, because one is like the first maximum and other is the second maximum, like max 1 and max 2. And for as you go up, you will see there are some children, and you need to get like update your own max 1, max 2. You can just use their values. Of course, the max 1 for this node will be the maximum of the maximum ones of its children, right? So you can just put any one of them, and as max 2, you will either take the actually you will take the maximum one from the other ones. That's it. So it will be something like this. And this way, at every node you will have max 1 and max 2, which is like what is the maximum depth and the second maximum depth in your subtree, but from different children, not from the same. Of course, if it is from the same, it could be something like this, but this does not really. I mean, for this V, we are trying to find the like a diameter, like the path, the maximum path which is passing from this V or in its subtree. Yes. So this way, if we just do this by this definition, of course, there is some node which have like the diameter in its subtree, right? So this way we will find I mean, if we do the max of max 1 plus max 2 overall nodes, it will give us the diameter. Okay. But probably the first one is easier, maybe. Okay. But this calculates everything in 1DFS. For this, you probably have to do many for loops, like find the maximum one and then start from that and then find the maximum one. Now you have the two nodes. Okay. Yes, this is like everything for the diameter. and it is, I mean, the knowledge for this diameter is required for the problem New Year tree. Started even. Right. So do you guys have any questions or anything? Okay, great. I will add more problems in the sheet and maybe put a star on the very important ones and you can solve them. I will add LCA problems, probably sparse table as well. I've added MST problems in in the DSU section. Okay. If you guys have any comments or any questions or any feedback, you can send me a message right now directly or in the public chat, or you can also send me a message on WhatsApp or Discord. Okay, if there are no questions, then the class is over. Thank you.